In this video we'll be looking at the conditional jumps that the processor can support, in particular the jump 0 and jump not 0 instructions. The previous video looked at the jump instruction. That's just an unconditional jump, and it causes the processor to jump directly to the specified address. The jump 0 and jump not 0 of course are conditional jumps, and the jump 0 instruction will cause the processor to jump to the specified destination address only if the result of the previous calculation was 0, and the jump not 0 will of course jump only if the result was not 0. So this is the simple test program that we're going to run. It starts by loading the accumulator with a value of 0. If the value that's tested, if the 0 flag is not 0, it will jump to the end of the program. It will then load the accumulator with a value of 1, test the value for 0. If it is 0, it will jump to the end of the program. It will then load the accumulator with a value of 1, test to see if that's not 0, and if it isn't 0, it will jump to the end of the program. And then if it gets to this point, it will jump to the start of the program. So in theory, what should happen is it should come down to this point, and this instruction, it should jump to the end of the program. Following this jump, there is a halt instruction, so the processor should get to this point and halt. It should never jump back to the start if it's working correctly. This is kind of pseudo code. It's just a way of writing down the program in a simple form. This is kind of the instruction or machine code version of the same, and this uses of course the values from the instruction table that give the code for each particular instruction. We need a couple of values for this program. We need a value of 0 and a value of 1, and they're stored in memory at locations 1111 and 1110 respectively. Okay, so we'll start the program running. The processor is already in the reset state. We're in single step mode, and we have the reset on halt instruction option turned off, so the processor will actually halt when it gets to the halt instruction rather than resetting. So the first instruction should load the accumulator with a value of 0. So we'll step through that instruction. And nothing much seems to have changed, but we did then explicitly set the accumulator to a value of 0. And it is important to make sure that you do complete any instructions prior to testing the flags if you intend to use the flags. When you boot up the processor, they'll have a random value in them. But now, because we've gone through the process of loading the accumulator, you can see that the 0 flag is actually set, and that matches the value in the accumulator register. It is important at this point to understand how the processor updates the flags. As with any microprocessor, there is a certain structure to the way it behaves, and it is important to understand that to get the most out of it. The flags do not relate to the value that's in the ALU register at the end of the instruction. The ALU register is an internal register that you never access directly. It's used implicitly whenever the register B and or register A values are updated. The important point being that following the loading of register B and register A, which will cause an arithmetic value result to be present in the ALU, at the end of the instruction, the value in the ALU is transferred through the data bus into the accumulator, which is why it's called the accumulator. It accumulates the value of each successive computation. Now, because the ALU is kind of a live system, it's not latched as such. As soon as you put values into the A and B registers, the ALU register will immediately be updated. If you think about that, what you're going to end up with is a value in the ALU register at the end of an instruction that does not necessarily match the accumulator. Might sound a bit odd considering that at the end of the instruction the value from the ALU is put into the accumulator, But what happens is, let's say there's a value of 1 in the B register and a value of 1 in the accumulator, that will give you a result of 2 in the ALU. But at the end of the instruction, when that value of 2 is copied into the accumulator, then the combined value will be 3 and not 2, because you'll have a situation where you've got a 1 being added to a 2, and that's what the ALU will then show. So the flags are actually updated immediately following the loading of the A or B register, but prior to the ALU being copied into the accumulator. So don't be surprised if you see different values at the end of the instruction between the accumulator and the ALU. That's just the way the system works. Okay, the next instruction is jump not 0 to the end of the program. So we do have a 0 value and the 0 flag is set, so we should not jump. So let's go through that instruction. So firstly we load the instruction. You can see we've loaded jump not 0. If we look at the program counter, it should not jump, and the destination address for this is 1100. That's the end of the program address. So if we now step through the remainder of this instruction, we're currently at phase 4, go to phase 5, nothing's happened, and then we're on to the next instruction. We've incremented to the next memory location and we haven't jumped, which is obviously what it was supposed to do. So the next instruction is load A with 1, so we're going to load the accumulator with a value of 1. So we'll step through this instruction. You can see we have the load accumulator instruction that's been decoded, and if you keep an eye on the 0 flag through the next 2 phases, you'll see that we've got the LA load accumulator and the CE, which is the enable memory. So we've enabled the ROM to put its data out onto the bus, and if we go to the next instruction, we'll see that 2 things happened. One is the ALU has updated in response to the accumulator being loaded, and the 0 flag's gone out because also we no longer have a 0 value. Although these 2 are the same in this instance, that is not always the case. They're only the same now because register B is 0. So next instruction is jump 0 to the end of the program. Obviously we're not at 0 because the 0 flag is not on. So if we step through the following instruction, we'll see it's decoded as the jump 0, but we shouldn't jump. So if you watch the program counter through this instruction, you'll see nothing happens. It stays at the current address. The next instruction is load accumulator with a value of 1. So we'll step through that instruction. So we've got the load accumulator. We'll go through the remainder of that instruction. We have a value of 1 in the accumulator, and the 0 flag of course is still off because 1 is not 0. The next instruction, jump not 0. So this time we should jump because the value is not 0. So we should not jump to the jump start instruction, we should jump to the end of the program, and that is address 1100. So if we go through this instruction, we see we have the jump not 0 LED on, and we've jumped to the 1100 address. The rest of this instruction doesn't do anything. Its 2 phases are void. But we are now at address 1100, and at address 1100 we have the halt instruction. The halt instruction being 1111. So we should see the halt. So we should see the halt LED illuminate as we go through this instruction. And indeed, we do have the halt instruction completed. And that's it, that's the entire program finished. We went through, it didn't jump when it wasn't supposed to, based on the testing of the flags, and then when it was supposed to jump, based on the testing of the flags, it did indeed jump to the destination address. And as expected, we never jump back to the start. So we know that the jump 0 and jump not 0 conditional instructions are working. In the next video, we'll look at the jump carry instruction. In the meantime, as I said before, if you have any comments or if you want anything in particular explaining, please leave that in the comments.